Hello everyone. I'm going to present the work that we have been doing at APFL and MTM in close and fruitful collaboration with PSI and EMPA on developing in-situ monitoring techniques by the help of using Operando synchrotron measurements of laser powder bed fusion, which also in turn help us to, in fact, understand also microstructural phenomena that are going on. Okay, it works. So my talk is going to be in three parts. It's going to start with Operando investigation of the regime instabilities under constant process parameters. I mean, this is the stochastic nature of LPBF process, but we're going to see some nice work on that, and also the application of acoustic sensorization to somehow alert us to some extent when these instabilities are occurring, because you don't want to have unstable keyhole while you optimize your parameters for staying in conduction, right? And then we're going to talk about healing of defects and the acoustic signature for it. And at the end, if I have time, I'm going to go through this in-situ Martensite decomposition in TX6 for alloys. Yeah, so motivation. I mean, we're all familiar with this microstructure of LPBF process. It's been fabricated unidirectional scanning, but the funny thing is that we all have asked this question from ourselves, that why these melt pools are always different from one another. So there are, I mean, of course, it's the stochastic nature of laser powder bed fusion due to these complex phenomena that are happening in the laser material interaction. So, to name some, one is the intrinsic heat buildup. Of course, the temperature going higher, the melt pool you create is going to be the starting temperatures, the temperature in front of the melt pool, basically. It can be the interaction of process byproducts. I mean, we know about entrainment of spatter particles. These are just flying around, and then they can shadow the laser itself, and you can have alterations in the melt pool depth. Another effect is the effect of geometrical features. Imagining you're going to scan a very thin wall connected to a bulk material with the same process parameters. Of course, you're going to have different melt pool geometry, and that can be also locally present when you create a stochastically lack of fusion defects, and of course, close to that, you're going to have the same effects going on. And the last one would be, of course, variations in laser dwell time in the beginning and the end of the track. This is a very well-known phenomenon in the process. So I'm going to talk about a little bit about keyhole regime, because we're going to go a bit deeper in what's going on. So keyhole is the product of excessive evaporation and the corresponding excessive recoil pressure that is overcoming the surface tension of the melt pool and creating this cavity, the depression zone. And by the time that you create the depression zone, you are activating the multiple reflection, which incorporates even more in deepening this cavity. Of course, we can see a nice movie which was from a previous science paper that was done by a group of Anthony Wallet, that they go as fast as possible. This is done in 5 megahertz, that somehow brings about new facts about keyhole formation and its corresponding properties. So this, in the keyhole mode, of course, due to this complex and high energy molten flow, there might be instabilities, there are instabilities, there's going to be collapses, there's going to be porosity formation, which are detrimental for the mechanical properties, and we would like to know if it happens, because it's going to happen. Of course, during this study, they showed that, or many studies that they used the in-situ imaging in the past 2 years, it's been clear that the keyhole front wall morphology is bringing, or the start of the instability comes from keyhole front wall morphology, which in turn results in the collapse of the keyhole, and then you have a newborn keyhole that, you have a newborn keyhole because of the detachment of this porosity. And then you're going to have the concentration of energy in that newborn keyhole, which brings about cyclic evaporation and formation of microjets that can impinge into the liquid with speeds of 13 to 16 meters per second. So if you have created and of course they have their own acoustic waves, they have an acoustic wave. And if you're having a porosity, what follows is the porosity collapse and rebound due to this hammering pressure. They call it water hammer pressure that can reach values of 140, 150 megapascal on one side of this small porosity. So, of course, we think that they create a sound, and we would like to see if we can hear it and somehow recognize it, time resolved, in the time resolved manners. So all these somehow scenario taking place based on what is recorded at frequencies of around 20 to 50 kilohertz. So the idea of the talk is to see if this generated acoustic wave can be used as a notion of this regime transformations or transitions in laser powder bed fusion. So I'm not going to go through it anymore. We use what Steven presented, the miniaturized LPBF apparatus, and we incorporated into with a membrane-free optical microphone, Zarion, that works in frequency range of 10 Hz to 1 megahertz. This should be, we thought this should be fast enough to capture such events. So this is the setup of the Operando X-ray imaging that we employed. So we, Stephen also explained a bit for the part of the diffraction that you can create walls. So you build a wall and then we somehow cleaned it from powders around it. And we went in the transmission mode at 0 degree. Usually there is an angle, but we went to 0 degree to get the highest contrast, to have a better visibility on the present interfaces in the laser material interaction zone. Because if you want to see the keyholes, you would also like to see the solid liquid interface and also the gas liquid interface as well. Okay, it was a white beam, 10 kilohertz of acquisition frequency, and a pixel size of 2.75 micron. Of course, the X-ray acquisition and the laser irradiance were in complete synchronization from each other. They were triggered at the same time. So doing some exploratory data analysis just by looking at the video, I hope the contrast is well enough. You can see it starts from the left to right, and the time is also right to left, and the time is also from right to left. So we saw that these regime transitions are happening. I mean, we can look a bit closer here. So you have conduction to stable keyhole, back unstable, stable, and then going to unstable keyhole. And you can see clearly, just by looking at the raw data of this acoustic signal, that there's a clear correlation between the start of these regime changes and these instabilities and what we see in time domain. Going at the frequency domain, time frequency domain, or the spectrogram, you can see these events clearly present, elongated in, of course, in the frequency. They don't have a particular frequency. This information is spread in a large frequency range. But one can say that most of this information are carried away at the frequencies of 35 to 105 kilohertz. So this was a starting point for us for filtering and signal analysis and so on. I'm going to show also another example here. We start, I use a white cursor here because maybe it's easier to help you find the meltpool. The meltpool goes exactly on top of it at the moment. So you're in conduction mode, and then we have the transitions to stable and then unstable keyhole, formation of small porosities which are left behind, impinged, pinned in the structure, and also and then you have also coalition of these smaller porosities which result in mini porosities. Looking closer again, you go to stable and then you are in unstable. So also, I mean, we have over 20-25 videos of these instabilities that we looked closely, and we somehow saw that there's a clear correlation. So we wanted to do it mostly or more a data-driven approach without using machine learning or deep learning algorithm, which is the fashion of the day. We wanted to just, because it's so clear, I mean, we don't need that, just a simple pipeline that can help us to process it faster and also react as fast as possible during the process. So, of course, we did normalization, filtering, moving average of this raw signal. We used softmax and cross entropy loss. So this gave us, based on the ground truths that you get from the video, we could optimize the filtering for every of these regimes. So for conduction, stable keyhole and unstable keyhole, you have 3 different filters that you're applying, resulting in 3 different signals. And then, of course, with softmax function, you see which signal is basically the maximum, and that's your prediction. That's the regime that you're actually in. And it works really good. I'm going to show a couple of examples here. We start from conduction, green, stable keyhole, yellow, and unstable keyhole, red. And just by looking closely, you can see that the prediction is the green line, and the ground truth, I mean, this is the binary data, even not looking at the signal itself is okay, that they have really nice correlation one to another. This is another one. Of course, we went to very slow speeds. There it was 40 millimeter per second. Here we are almost 3 times higher, 4 times higher, 150 millimeter per second. We wanted to go faster to also show this effect of speed. Because there should be a scanning velocity notion that if you go as fast as possible, probably you're not going to let these instabilities happen so much, or you need, of course, also faster imaging. So we have to stay somewhere that is relevant for generating the ground truth. Okay, so we did, for this study, we did 15 videos, investigations, changes in the laser process parameters, beam spot size, and the defocus direction as well, going negative direction, positive direction. So we try to discover all these possibilities that are usually not really looked at. A blind cross-examination was performed, so every time we took 14 out of these videos, we optimized the filtering process, and then we applied it on the one that was left out, and we did it for all these videos, so it was always a blind test. And then we used F1 score value to measure the cross-examination. I mean, this F1 score value is the harmonic mean of the precision and recall. So precision is how many retrieved items are relevant, and recall is how many relevant items are retrieved. So if we consider only 2 regimes, keyhole and conduction, we got extremely high values because the maximum is 100% for conduction and keyhole, so we were almost always accurate with a time resolution of maybe some microseconds. I would say maximum 100 microseconds, which is the time for one image, basically, in 10 kilohertz of imaging. And if we consider the 3 regimes, conduction, stable keyhole, and unstable keyhole, is still an acceptable F1 score, but most importantly is the unstable keyhole, when the porosity happens here. Here you want to be high, and that's what happens. So, of course, you are able to see this as stochastic unstable keyhole. You detect it by acoustic emission. You know where it happened, when it happened. Of course, it's time right now to go and heal them, right? So you can use a defocus beam, a positive defocus beam, so you can create these large melt pools that can go as deep as the previously created keyhole without creating additional defects. But can we detect that also by acoustic emission, this healing process? And that's the question. So we have this keyhole mode, and then of course this defocus beam comes and tries to wipes out everything. You can see the videos, it's like a vacuum cleaner that takes everything from the bottom cleans it out. Of course, there are some regions that these pores that come up, they don't have enough time to get removed and they remain in the piece. So this is an example of the methodology for the signal analysis. It's a perfect example because we have only removal of one pore. You can see, yeah, the video, yeah, I mean, now you can see it, yeah. Only one pore at 262.2 milliseconds, so you can see a spike in the raw data already going in the time frequency domain. Still, there's an event happening exactly at the same time in the frequency range of up to 100 kilohertz. And then doing the filtering, you can see that it's there. You know, the signature of the removal, it's there. And it's very clear, very clear. So for this study, we did windows. We got the acoustic signal into windows of certain points, certain sizes. And prediction and ground truth, if both coexisted in that window, of course you get a score of 1. And if one exists and the other one doesn't, you get a score of 0. So here we did 6 videos and 94 point removal events. And you can see the results. It really depends on the window size and the resolution of noticing this effect that you would like to have. So you can say, okay, this region is not important for me because my scanning speed is not that fast, not that high. It depends on the distance basically you're traveling in every one of these windows. If it's one layer for you, one layer matters, and then you would like to go to the same layer and heal it, then you can use the biggest window size, and then you are absolutely sure if you're removing any of these defects. So I have some minutes more. So we did 2 minutes, super fast. We did one study on the TI-64 due to this, Stephen already said, alpha prime martensite structure. You would like to heat treat it, but we wanted to see if we can do it in situ. So we did we used the normalized enthalpy notion, which is the energy balance between input and dissipated energy. So theoretically, if you stay below 1, you shouldn't melt. And this is why we went with the normalized enthalpy values below 1, and we did heat treatment for 30 seconds. And then after the heat treatment, the beta was transformed back to alpha martensite, and they couldn't retain it. So we did some simulations with somehow incorporating the slope to the modulation of the cooling rate by gradual decrease of the input energy into the process at the end of the heat treatment. So these are the results from the simulation, and just by looking at the cooling rate in the older case and in the case that we just improved, you can have changes from 3000 Kelvin down to 400 Kelvin per second, which is completely relevant for the transformation that we are looking at. So we repeated the measurements with the modulation of the cooling rate, and you can see that we were able to retain the beta inside the microstructure. I think I'm gonna stop here, maybe, so there's time for the questions, but we can discuss, of course, after the presentation if you want to know more.